So I start.
Exactly. You can share the screen now from the home screen, Marcin.
Okay, so you will start from the very beginning, okay?
Yep.
And then you should see it. Okay, I just need to. Yeah.
Perfect. Thank you to those that have begun joining. Welcome. So we will give it around 3 or 4 minutes, and then we'll make a start. Thanks again for the the many of you joining on. We're going to give it around another 2 minutes before we make a start. But welcome and thank you for joining. Welcome from Indonesia. Welcome. So welcome for those still joining. In around another minute to 2 minutes, we'll make a start. Thank you for all those still joining. We'll give it 1 minute and then we'll just make a start for it. Okay, I think we'll make a start. So, well, first of all, thank you to each and every one of you that's joined on today's workshop. The response and attendee demand has been truly amazing. So thank you. So good morning, good afternoon, good evening. We have, I think, attendees from pretty much every part of the world, whether it be Indonesia, China, Taiwan, Australia, the Middle East, all parts of Europe and North and South America. So thank you and welcome. My name is Angus Long, working within Skanwear. So this is our last and final electrical safety workshop of 2020. What a year. So it's been an interesting year and one that has been one of great opportunity, but also one that I'll be pleased to see the back of. However, for many of you that are on today, you'd be aware that we've been running these totally non-commercial electrical safety workshops, free to attend throughout the duration of this year, and the response has been truly amazing. So very briefly, Skanwear is an organization that manufactures and distributes arc and flame protective clothing and PPE, 78 countries around the world, with people in 9 different regions globally. That's enough on Skanwear, and that's pretty much all you'll hear. So we're moving now on to the topic, which is electrical safety in data centers. And I was privileged to be able to work with Martin Talbot, so working within Equinix as a senior mechanical and electrical engineer. And Equinix obviously being one of the global leaders in from a data center perspective. And then Marcin Ruta, who pretty much all of his life working on or near live or potentially live electricity, and within Eaton, GE, and now within his own organization, MR PowerTech. All of you would have seen what the agenda is going to be for today. And so with that, and well, before I move on, there will be a recording made available of this event and sent to everyone that registered and also those that attended. There will be a CPD, a CPD certificate for everyone likewise that's attended. Any questions that you want to submit, put them into the Q&A button. So at the bottom of your Zoom panel now, you'll see a Q&A box. You can click on that button, submit your question. We'll answer them throughout the duration of the workshop or at the end. So with that, I'm going to move on to Mr. Marcin Ruta. Welcome, Marcin, and over to you. Thank you.
Good morning, ladies and gentlemen. My name is Marcin Ruta. I'm a power system engineer and I do electrical network studies. And great thanks to Angus from Skanwear for the invitation for this webinar. And today I would like to show you challenges and solutions in data center electrical projects, at least from my perspective. Just to give you a bit of an overview what we are going to talk about. Well, actually there are 2 groups. We talk about the 11 kV part of the network and then things around the UPS on 400 volts. And as we know, electrical system, we can have multiple threads and like electrocution, electric arc flash, electrical fires, and so on. And today I will focus on arc flash purely. And since we have limited time, I just have to warn you that I will assume that we all know what arc flash is, and I will skip all the introduction on the topic. We'll just dive into the specific problems and all questions. I will try to answer on the Q&A session after presentation. So let's start. So far, this is the best recording I found on the UPS failure. So it's easier to show you. I believe it's good from an education point of view. It was very minor accident. However, if this will happen on someone's face, most likely it will cause 2nd-degree burn. And since we don't have a lot of time today, I will just try to highlight mitigation techniques that we can utilize in the passive and active solutions. So obviously you can obviously you can see that we have settings improvements. There's a base cost-effective solution. We have fiber optic arc detection, arc flash relays. We have arc quenching devices, and also ARMS, arc flash reduction maintenance switch on the low voltage part. We also can build our switches according to the Dayton arc classification for the medium voltage and arc resistant for the low voltage. So that helps. The second group will be adaptive settings. So that's a specific for scenario, and we'll talk about it. There's also selective interlock. Short circuit current adjustment is a very specific topic, not always utilized. Lockout, tagout, of course, remote operation, remote tracking, SCADA operation, that's all nice to have. And there are some other tailor-made solutions, very specific for some specific projects. So let's go. So we look on the data center network. Of course, this is not a fixed configuration. It depends on the company, it depends on the project. But from our point of view, we would like to focus on the worst case scenario and actually on all of the scenarios that we can find. And in this situation, just to highlight it, we can supply via grid, we can supply via generator, we can have supply via tie breakers, looking just on this area and some minimum maximum combination. So before we jump further, I just want to give you the question. So where would you expect to see a higher incident energy? Will it be at low voltage part of the installation or at the medium voltage part of the installation, 11 kV? And to keep it short, take your time to vote. And we'll keep it for a few seconds more, and then we go for the answers. Yeah, so it's quite good actually. We will see it at the low voltage part. And I will show you in a minute single line with the results, but we had multiple scenarios. As you can see, the generator operation was divided in 8 generators at the same time to the 2 generators at the same time.
Marcin,
and as you can see, yeah.
To be clear, the scenario that we are looking at now is an actual live case study scenario that you yourself have worked on.
Yeah, if I didn't mention this before, all of this, what I'm talking about, those were real projects that I was working on. So that was real situation. And as you can see in the 2 generator operation mode at the low voltage part, it was quite dangerous. And I will explain in a minute why. But at the same time, what is unlogical, you will see that on the 11 kV side, this is actually one of the best scenarios that we can have. So those are not logical results. Just to give you an overview, that was the model for this specific project. We have the 2 supplies, we have generators, multiple generators. And at that time, 2 generators were likely to happen as the beginning of the project. And what you don't see on the previous result, that on the line side of this main breaker on the low voltage side, we expect 118 calories. That was crazy amount. It's very high number. So we have to do something with it because this area will be very bad to work on. So we'd like to avoid it. So some examples and solution. And before we go into it, most of you will be aware about the hierarchy of controls from NFPA 17E. So we start with elimination, we end up with the personal protective equipment, last but not least. And I like to add to it that we need also identification, because we would like to know our numbers first before we jump into any improvement solutions and problem solving. So once we did here, what we can do, we can adjust the settings, we can do some hardware solutions that I mentioned before. We can adjust some working procedures to make it safer. Or we can maybe modify operation modes, which is not feasible most of the time. So to give you background why we have 68 calories in this specific location, I have to just point you on the time current curves. This is a low voltage breaker tripping curve. That was medium voltage, just for this specific scenario. And from 2 generators, what we expected to see initially was something approx 14 kiloamps. And if we recalculate it back to the arc current, it will be something around 10 for this specific project. So that was very low number. And if you can see here, that's what I highlighted here, the breaker had a problem to trip it at all. It will not detect this. And the time was not even 2 seconds, it was more than 20 seconds. But just for, as an NFPA, we use 2 seconds to stop at this specific project. And the maximum we can expect was 57 kiloamps. So just to fix it, the first idea was to modify the low voltage breaker settings, but we found that there is some limitation because it was very low arc current, then we barely see any difference. So we still are somewhere in this 2 second area as a fixed. Normally it would be around 20. So it didn't really help very well. The same situation will be if we use zone selective interlock for this specific situation, for these 2 scenarios. For all the scenarios, this will work very well, but not for the 2 generator operation mode. What I found, okay, maybe we can modify also medium voltage related was the 1 step ahead, go upstream. And there is a reason why I show it here. You may see there's zoom. So I dropped the settings on the medium voltage relay very low. And this is obviously not selective. This will cause the problem with the transformer starting due to inrush current. So we cannot use something like this. But we know that if we keep it, we'll go below 3.4 calories. So that's a very big difference. And now I'll come back to this example in a minute. So the next step was, okay, then can we use ARMS, arc fast reduction maintenance switch, for this specific scenario? This will be perfect again for the other scenarios. We improve situation a lot. And just to explain a bit what ARMS is, it's a switch, that's what you can see here, that we activate when we would like to do some maintenance work on specific part of the switchgear or on the switchgear itself. And it will drop the settings to the minimum level, predefined or default minimum level, depends on the device. And however, we have to remember that this will reduce energy on the bus or load side of the breaker. And again, this was not really very useful because if we go to the minimum, we were still at the same situation as here. So it was not really direct improvement. And why we are here, I want to just explain a little bit about the line and load side concept, because it's important when we talk about the ARMS. ARMS will be implemented in the low voltage breaker. So everything what we do with the low voltage breaker in this situation, is it setting adjustment? Is it ARMS? Whatever it is, it will affect only load side of the breaker, so everything which is behind the breaker. And everything what we do with the medium voltage relay, which is installed upstream, somewhere in the medium voltage switchgear, will affect transformer, cable, and the line side, and actually the bus side also. So to put it in the graphic perspective, physically depends on how the switchgear is built. This will be line side in our situation, and everything behind the breaker will be called load side. So once we have this clear, we are back to the example with the medium voltage relay. But in this case, what is called adaptive settings. This is maintenance switch or arc fast reduction maintenance switch on for the medium voltage. Physically, what we do, we reprogram the relay, protective relay on the medium voltage side with additional group of settings. This will be activated by the logout tagout maintenance switch, which is physically the switch, but need to be logout tagout. And it looks the same because it is the same settings that I used before. But intention is, as with ARMS, to use it only during maintenance operation, maintenance activities. And this will reduce energy a lot, in this case below 6 calories per square centimeter, assuming that in total it would take something around 100 milliseconds. And once we are done with our maintenance operation, we are reversing it back. So Martin will explain a bit more probably about the procedure, but this will be one of the solutions. What we very often see in the data center projects, which at least we will see the transformer differential protection or the bus differential protection. And this protection can improve situation a lot. And very important point to mention here, because it makes a big difference, is how we install the CTs. So just to focus on the low voltage area, in this case, if we install CT, let's say closer to the bus bar, so behind the breaker, everything that happens on the line side or load side of the breaker in this compartment actually is in zone, which will be very fast for tripping. So we expect something like 5.8, below 6 calories, maybe less. However, if we install physically the CTs before the breaker, so we still have this area of the bus bars, which are on the line side, which are not in zone of the differential protection. It means that in the one compartment, we can actually have 6 calories for 20 centimeters before the CT and 68 calories for 20 centimeters after CT. So that's something to consider also if you have a single line faults. And for the differential, depends how the system is grounded. Is it insulated system or high resistance? It may not pick up in zone faults even. Depends on configuration, of course. So if you go to the hardware solution for this specific problem, we can have a fiber optic arc detection. And because it's fast and it's separate system, we don't have any problem with selectivity with it. And we can keep the system relatively safe because it's still something, but it's 3.4 calories in this situation. And so let's say below 4 calories. So it works very nice. The same system can be equipped also with the arc quenching, which is a very nice solution. Depends, doesn't matter who is doing this. It's a very nice solution. It has to be very fast, less than quarter cycle, so less than 5 milliseconds. to keep system below 1 calorie. And what is worth to mention here is that this is the only system that, when we talk about the arc flash, it protects people and equipment as well. So I'm not going to describe it, it's better to show it. There's a system with it during the fault, and there's the system without. Obviously made a little bit tune up for the presentation, but you got the point. So the same thing we can do for the discussion we have for the UPS, and that's what I saw in the different projects. If we talk about the UPSs, we usually expect 3 operation modes. So one is the UPS only, so the UPS can sustain the fault for something like 50 milliseconds, maybe less. We can have a static bypass built in, which usually goes 300, 400 milliseconds, maybe more, depends on your system. And we have manual bypass, which is very common to see. I would say 99% you will see it. So again, small question, where you expect to see higher incident energy? In which scenario? In UPS, static bypass, or manual bypass? We can keep it for a few seconds more and then 1, 2, 3, 4, finish. Yeah, close by, but not fully true. What we will see, most of the time we'll see the problems in, as most of people said, manual bypass. That's very clear because of the high energy that will be transferred, but also about the tripping time in this specific project, of course. And UPS static was 400 milliseconds. We expect 19 calories. This is on the UPS side, and this was on the low voltage switchgear, let's say line side of the UPS and load side of the UPS. That's how we can call it. I will show you on the single line. That's easier to see. So what you can see, that's the UPS mode. So we expect 0.6 calories. Let's say we can skip this one. There's nothing to improve it. We have UPS with static bypass, just on the UPS internally. And then we start to see 19 calories. And I'll explain why. And then we have a manual bypass with 29. So our biggest concern are those 2 scenarios. So just to go through it a bit. So 0.6 calorie was not a problem. We focus on the 19 calories. And that's because it will be unlikely for your UPS to work only in UPS mode, because we don't want to have a system or UPS to shut down for every small fault downstream. And for the automatic disconnection TNTT system, we need 300, 400 milliseconds as a minimum. So just to explain a bit why. So if you maybe saw here, we have parallel breakers for each UPS. It's not my design, that's what I got. And if you will see, the breaker is faster than UPS, it trips in 230 milliseconds, that's okay, but we'll end up with 19 calories. So we can improve it by fiber optic arc detection because of the selectivity challenge here. We can also adjust the settings a bit, but it won't be a big difference. Also, the line side of this UPS breaker was slightly higher because of the 400 milliseconds and was, I think, 25, 26 calories in this specific example. If we go further, we have manual bypass, and manual bypass was the highest energy. And in this case, I was looking on the arms and fiber optic. Physically, it looks like this. So with arms, we can go down to 4.7, and very similar will be for fiber optic, 4.7 calories, because they should have similar time to trip. And it was possible to set it like this. So there's a big difference from 29. And just to give you a comparison how it looks like between the system with fiber optic and without, because that's very nice on cell. You can see the difference between 500 milliseconds fault and 50 milliseconds fault. So that's quite different. And I don't know if this will be mentioned, but this one was something like on the left side, 12 calories, and 50 milliseconds was 1.2 calories. Well, I think that's a straightforward explanation how it works. And I hope you enjoyed, because that's all the time we had. Now I would like to pass it to Martin Talbot. Thank you very much. All the questions I will answer later in the Q&A session. Enjoy.
Thanks, Marcin. I'll just share my screen now. Okay, that should be me sharing. Good afternoon. My name is Martin Talbot. I'm just going to follow on from what Marcin was speaking about, and what I wanted to do is go through a sort of scenario of a complex isolation, and that will bring out the talking points of electrical safety in the data center, with a particular nod to arc flash hazards. Okay, so what we're going to look at as our scenario is that we are going to safely isolate a low voltage switchboard for maintenance and cleaning of internal to the switchboard. An external contractor will carry out the maintenance. Your own employees will isolate the switchgear ready for the work, and the customer supplies must be maintained during switching operations and work. Because we're a data center, major part of our business is supplying customers with power. We want to do that continuously and safely. The first part of that is about receiving the risk assessment and method statement from our external contractor that's going to do the work. So fundamentally, we want the RAMs to say the who, the why, the how, and the when of how they're going to do it. We want them to be specific and not generic. For an example, I always want them to have only the specific safety aspects of the task in hand. If there's no working at height aspect, I don't need pages of working at height documentation in the RAMs. Make sure you understand them, and that your contractor fully understands your requirements as well. Once we've got the RAMs and we've agreed a day when we're going to do the job, what we want to do is going to prepare a safety program or some kind of engineering script. And it's going to tell us how we're going to safely isolate the switchboards. Always recommend having some kind of safety program or engineering script for doing something complicated. And by this, what I mean by complicated is a high energy switchboard with more than one source of supply that you could get wrong. So you could either, at worst case, hurt someone or drop supplies to a customer. So it identifies all the equipment that we're going to operate, the points of isolation, how these are secured, what equipment we need to do this, keys, locks, signage, test equipment if required, and then we're also going to cover the restoration afterwards. Yeah, so again, following on from Marcin's schematics, this is sort of a typical UPS input and output board scenario. And why I've chosen this is, like Marcin says, the LV side potentially has the most dangerous aspects in respect to arc flash. It's normally got the highest incident energy, particularly where we've got transformers which might be close coupled straight onto LV boards. And that reason is that we get the high current. The voltage is there to push between contacts to create the arc, and then the high current is really where the release of heat energy comes from, that does damage to personnel in the immediate area. Unlike HV equipment, LV equipment is rarely rated to deal with that kind of blast. MV or HV equipment might have an AFLR rating. It's sort of unusual for LV to be type tested to that degree. Okay, similar to what Marcin said, we've got a 3 UPS parallel system, redundant system, with an input and output board configuration, manual bypass and static bypass. And this is our point of work that we want to safely isolate to shut down and clean, but maintain supplies through the manual bypass for the customer. So when we're going to do this, we're going to transfer all of our load from TX1A to TX1B. to begin with to get our UPS into supplied by one system. We're also going to transfer our system to generators. So it's important to know, how is our protection system set up? Does that make any changes in respect to the arc flash considerations that we've got? The generators provide more or less incident energy. And what I'd always advise is that you set up your safe system of work in respect to arc flash to always have the worst case scenario considered. So as Marcin said, it's going to be an UPS bypass. It might also be from generators, and that will be always your set level. The worst case will always be what you set your safe system of work to. When we're doing this switching, we always want it to be, as you know, we don't want personnel in front of the switchboards operating the gear as far as possible, unless they have to be. So where possible, specify remote switching and get your employees to carry out that remote switching. Might be in the same room, but as long as they're not stood in front of the panel or switchboard, that's always preferable. Okay, so once we've transferred to the other side of the transformer via the bus couple, we're going to close onto our static bypass supply. And this bypasses the inverters of the UPS. All times we're ensuring that we've made good supply through to the customer at the bottom. Then we're going to close the manual bypass in parallel with the static, ensure they're in parallel, and then open the static bypass. And we've transferred our supply through to the manual bypass. We're then free to begin isolating this side of the board. We want to isolate the batteries as well, because they're a possible connection onto the main switchboard that we want to isolate. And also batteries are another hazardous area, but it could produce not just electric shock, but an arc flash hazard. We need to make sure that we understand what that risk is and have we provided the correct personal protective equipment to deal with that. Then we can disconnect the switchboard, shut down the UPSs correctly, open up the transformer incomers, and make sure that we're fully disconnected and the bus coupler at this stage. However, because again, as Marcin said, the line side and the load side, we want to make sure this side is also isolated. So we have to isolate at MV on the transformer side as well. Okay, and then it's earthed. So all of these steps are what we want to do to safely isolate our switchboard. And we put that inside of a safety program. Also inside this safety program, we want to include the things that Marcin was talking about in incident energy switches or reduced energy switches, however you want to turn them. We want to turn them off at the right time at the beginning of the process, so that when we're switching, we want to keep incident energy low. But also, just as important, we want to turn them back off again when the process is complete. Because if they're left in the on position, that our protection system is no longer selective after the maintenance is complete. Who should create the safety program? It should all be created by someone suitably qualified and experienced in your data center, in your electrical system. And who should check and approve the safety program? Again, someone who didn't create it, a second pair of eyes to check and make sure that's correct. And then there should be a routine of storing completed safety programs and auditing them after they've been completed. You may wish to consider using switching tags. I always would recommend having a dry run. So once you've created your safety program, you do a run out of it, a pretend run, to make sure that you've got everything correct. All of your switching references are correct. And an extra level of safety is adding what we call a switching tag. So these are small parts of the safety program. So for each individual switch or piece of equipment that you're going to operate as part of your safety program, you have a tag showing the steps that the operation carries out and the correct name and reference. And that's applied to the switch. so that when you go and operate it as part of your safety program, you can check on the safety program, step 10 at UPS room 1, output switchboard run, supply to UPS 1.1 MCCB. I'm going to switch this off. My accompanying safety person agrees. The switching program and the switching tag on the switch align. We know we've got the right switch, and we're eliminating human error and opportunities for mistakes. Once we've done that, we've got our switching program, our RAMs are approved, our switching program is approved.
Martin,
yes.
It's a very interesting point you just raised, and I'm not sure that I've really seen that before. So excuse my ignorance, but I'm not aware of that many other organizations doing that. Do you feel you're unique in doing that, and why did you decide to do it?
I don't think we're unique in doing it. This isn't something that we've invented. This is not that common, but this is all about eliminating human error and having that double check of what switch that we're operating is correct. Its primary driver is maintaining supplies to the customer. But if you're maintaining supplies to the customer, it means we're not having accidents that cause disconnections.
That's good. That's excellent. Thank you.
Okay. Okay, yep. So we can then begin our switching. Once the RAMs have approved, we're happy with the contractor who's going to do our work. We've got our safety program, we've got our plan, we know how we're going to do it safely. Customers have been notified, dry run has been carried out, and if we're choosing to use switching tags, they're all in place. And we can go on and carry out and do safe isolations. For safe isolations, all the standard rules apply. We need a good system of applying safety locks and good control of keys. You know, accounting for who's applying for keys, where the keys are held, who's got them, and things like that. We shouldn't be using safety locks for decommissioned circuits, in my opinion. Safety locks are there for when isolations and work are being carried out. If you go along any switchboard, the only time you should see a safety lock in place is when work is being conducted. If you've got decommissioned circuits being effectively decommissioned by a safety lock, I don't believe that's right. That circuit should be pulled back from the circuit breaker or isolation device, so it can no longer be connected, and then the safety lock can be removed. Okay, so when we're carrying out switching, we want to be wearing the correct PPE. So during these times, the risk of arc flash increases because the risk of human error increases. We might have just carried out maintenance. There could be a problem, tools, whatever. All these things that we should avoid, but sometimes they don't. So that's why we increase our protection. So we wear head protection for switching, gloves for carrying out switching if we have to do it in front of the switch gear, and we're always wearing the correct rated arc flash PPE. On proving dead, again, we may need to increase our protection in respect to arc flash. So not just having rubber insulated gloves to protect us from electric shock, but also a leather or any other type of glove that is heat and flame resistant. The best process that I think for doing this is that when you're proving dead, the person proving dead should be the only one in the arc flash boundary. The accompanying safety person should be at a safe distance outside it, but still there to render assistance if required. He then proves dead. Once he's confidently proved dead, all arc flash restrictions can be relaxed because there are no exposed live conductors anymore. So that means that he can then escort a contractor to the point of work and then confirm dead to him without the contractor having to wear any additional PPE. Once we've proved dead, we're going to release it for work or testing. And to release it for work or testing, we need a robust documentation system, the electrical permit to work. And that's going to allow a competent person to go over the steps that they've taken to make equipment safe and prove that to the person who's going to take charge of the work and carry out the work. It gives them that extra opportunity to go over the steps and make sure that everything's been completed. So on that permit, we want to clearly and concisely define all the work to be carried out, identify the points of isolation, and use specific circuit references and locations. You need to know any additional safety measures, such as special instructions, exactly like the confirming dead procedure that I just described, where our worker proves dead with full arc flash PPE within the arc flash boundary, and then goes and confirms dead with arc flash restrictions relaxed to a contractor who doesn't have the same type of equipment that your employee may be supplied with. And then ensure references for method statements and risk assessments and switching schedules are always correct. Okay. So once these been signed over, your worker can carry on and do the work that he's been brought in to do. And then once that's completed, the restoration supplies can begin in accordance with the safety program that you've already produced. So that's just a very quick overview through a job, how there might be some arc flash requirements. I just want to look at some live working aspects that might be present in data centers. So live work is only permitted under exceptional circumstances, and that should be in any industry or any building. Any live work must be authorized by someone suitably qualified and experienced, and a risk assessment should always be conducted before any live work is permitted. An example is always fault finding, and the other sort of data center specific example you might consider is terminating new customers into power distribution units. Whether this you consider this live work or not, terminating a new customer into this panel, it's not practical, obviously, for us to shut this entire panel down and all the customers on it to add a new customer onto it. But we risk assess it. We make sure that we're in the correct PPE that still allows them to do the task, and we understand the hazards involved, such as the fact that most common faults are line to ground faults. So at that voltage on this panel, it's 230 volts in the UK. In other countries, it might be 150. And at that voltage, it's very difficult for an arc to sustain and then produce the heat that causes damage to the area. And any three-phase conductors are generally always enclosed, and we provide them with the correct PPE to do the task. Again, within the data hall, some important questions that you need to ask are customers' IT technicians suitably qualified and experienced to configure power to their equipment? Is that under the customer's responsibility? Has equipment been installed by the customer been electrically tested? And are customers aware of and adhere to your organization's permit systems when they are in the customer space configuring power? Selection of PPE. As Marcin said, PPE is not the solution. It's an insurance policy. All the processes leading up to the job and during the job should ensure that personal safety. The PPE is an assurance policy against things that are outside of your control and to limit life-changing injuries. The best way to keep people away from arc flash hazards is to locate them remotely away from it. And that's by remote switching, either by using control panels, SCADAs, or in some cases, umbilical devices. Before you want to do an arc flash study, you want to look at what's appropriate for your personnel to wear. Where are they wearing it? What areas? What tasks are they doing? Have a look at the market. See what's there for people to wear. And what would you be comfortable with them wearing? Then you can go to someone like Marcin, who's going to do an arc flash study, and look at your electrical system and say, can our electrical system fit within these limits for this PPE? Is it safe? And it's about protection versus comfort, because as well. There's an additional trend in data centers where they're beginning to run hotter, and then it becomes more difficult to enforce people to wear long sleeve, thick, fire protective clothing. But there are advances being made. The clothing is getting lighter and better to wear, but it's just about that understanding and that balance between ensuring people's protection and ensuring people it's appropriate for people to wear and that they will wear it. And I think that's going to conclude my part of the presentation. And I think we're open for questions now.
You couldn't have timed it better, Martin.
Oh, good.
I don't know what you all thought. I thought it was excellent. As always with the workshops, probably the one complaint we have is that we pack so much into such a short space of time, but I trust you found it informative. Now, there's a number of questions that have come through directly to myself through the chat and also through the Q&A. So I don't know if we let's maybe we'll go for the Q&A to start with. So Gary Thornton has raised a question: when using safety tags to track the order of instructions, would you recommend that the safety guy accompanies the switching engineer at the point of work, or is remote, say in the NMC, tracking on a schematic and any monitoring systems that may be in place? I think that's for you, Martin.
Yeah, I would say at the point of work, to be honest. When you're identifying the switch to be operated, you both see the safety program, and it's just that second opinion. You don't really always get that. If you're telephoning someone up, they're not really giving you that second opinion that you're in front of the right switch and you're operating the right one. However, when he goes to operate the switch, the accompanying safety person should make sure that they're at least stood back out of the arc flash boundary, so that if anything does go wrong, they're not injured themselves and they're able to render assistance.
Excellent. Thank you, Martin. The other one's coming through about leakage current. Can it happen at the UPS system or not? And then what will we do to reduce, fix it, and protect if the leakage current is at the UPS? I don't know if you want to take that or Marcin.
Well, that's not exactly related with the topic we talk about. It's more those physical issues, and it's not really safety related at this moment. It's more like electrocution that you can have, but you still have a protection in the UPS.
Good. So
in a very general way to answer it.
Very good. Thank you, Martin. I'm just trying to pick up some more of the questions. So give me one moment. So I'm trying to look here. There was a view on adding new tap boxes to overhead bus bars and whether this requires arc flash PPE or not.
Well, is this dead or live? Well, I'm going to assume that if you're going to add tap boxes to a bus bar, you're going to do that dead. So the bus bar has to be made dead. During the process of making the bus bar dead and proving dead, arc flash protection should be a consideration, whatever the rating is. And then once it is dead, it's a dead bar. So you don't need to wear clothing during the operation.
That's good. Sorry, do you have another point to raise there, Martin?
No, the simple answer is yes. It has to be.
Good.
Doesn't matter which way you go, you will need it at some point.
Good. Another question is ACB enough for arc flash protection, Marcin?
Well, most of the time it will be, but it's not that you will see it's way below 1.2 calories. So it's very good for reducing. And I assume that when we talk about the ACB, so main low voltage switchgear breaker, like 2000 amp, 4000 amp, things like this. So it will never reduce the energy to the safe level, but it will reduce energy a lot if you use it properly. But by itself, it's not.
Good. Another one which come through was what makes the difference for LV to be more dangerous?
Yeah, the main point is that on the low voltage side, besides all the technical design that you see much higher short circuit current, of course, the problem is with the tripping device. Arc flash has a more or less very similar voltage drop across itself. It's vary a bit, but more or less it's similar. So if you have on the 11 kV, even 1000 volts voltage drop on the arc, it's not a big difference for the arcing current. But if you have the same on the low voltage, let's say in 400 volts, you have something like 100 volts, 120, 150. That's a significant difference, and you see very big difference in the arcing current at the end. And this will cause and usually is the problem, is a tripping time. So that's the main issue, extended tripping time and much higher current on the low voltage side.
That's good. Another question that come through, which I think you'd kind of answered, Marcin, but was around, I think it was related to field service engineers when they are working on equipment installations that haven't had the arc flash calculations on. Well, just from our experience, so we've worked extensively with a number of different clients on trying to resolve this very issue. So there are a number of supporting documentation out there where one organization, for example, have got some very elementary understanding. So they've created a matrix which is looking at the voltage, the rated voltage, whether it be AC, DC, upstream, overcurrent, circuit breaker devices, and the short circuit current. And then you may say from some basic components, they can begin to have a as good as possible understanding of the level of protection that their engineers should be wearing at any one of those points. Very simple to understand. Of course, it's not foolproof because it's working very much on predictions and the data that is available, but at least it's better than nothing, because understandably, when you're working in a field service environment, it's very challenging working on customer equipment when there isn't this level of arc flash calculation studies available. An interesting question has come through, Marcin, which is, had several arc flash surveys from independent and had highly variant results. So what could you say about that, Marcin?
Well, it can happen. Well, technically, if you have the same input, you should have the same output. And that's what I always mentioned, that very important is the input. So whatever you put in, that doesn't matter how you do it. If you put in the real data, proper data, you should have the same results. There may be some variation, of course. So you don't use your results very strictly to decimal point. It's like if you have 23 calories, you try to use something which is 25, 26, whatever rating is possible. We don't go strict. We always give some 10% variation on top of it. But in general, if you have something like this, then something is not okay, because you shouldn't have that big variation in the results.
Okay, it's good, thank you. Another question was, we have a few clients who use Umbilical to turn on newly installed TOUs. We do not always get the opportunity to isolate bars in live data halls. Martin, do you want to say that one?
Yeah. What's the question?
I guess the question is around isolation when it comes to having to work live.
I think you have to look at
what I can do here. What I can do here to probably help you is, so let me just quickly see who had raised the question. I think it was
Steve Watson. I'm looking at it now. Yeah,
I can probably unmute him so he can probably speak for himself.
Would like to have an answer.
I don't know, Ben, if you can unmute Steve Watson and he can articulate his question.
Yeah, fine, one moment.
Steve Watson, you're coming on stage. You should be able to unmute now, Steve, and talk.
Yeah, thank you. Do you have any examples of umbilical equipment for these examples in data centers where the isolations are not achievable? For example, we've used such an item called a chicken switch recently on a project.
Yeah, generally you only use those at MV. So that's for a MV circuit breaker that we didn't want to stand in front of.
Yeah.
Within the data hall buzz bar, any kind of PDU arrangement, if we had to do anything on the three-phase element of that, it would be shut down. We would do a shutdown, because even your customer should be supplied from A and B. We would have to tell them that we would have to lose a supply in that case to do that work, because it's too risky otherwise to do that live.
Yeah. Okay.
Does that help?
Yeah. Fine. Thank you.
Yeah.
Thank you, Steve. So got another question coming in here. Is can an arc rated visor be used safely without the correspondingly rated balaclava? I'll answer this one. You may answer this slightly different, Martin. When it comes to PPE,
it depends on the visor, I think.
Depends on the visor, but strictly if you're working to an FPA 70E, which a number of organisations would be, then it would stipulate the use of a balaclava. I also think it depends upon what the instant energy values are, and it's about what is practical. What we're finding increasingly in the industry is that there is what the standard says, stipulated by an FPA 70E, but also you need to balance that off with what is practically being used by the engineers themselves. And so it's all very well saying that a balaclava must be used, and it should be used, particularly when you're moving up to anything above 8 cal and onwards. But I think the importance is having a visor that's got a suitable wraparound around the side of the face and chin protection. Martin, you can answer this one.
Yeah, it's again specifying a PPE, like you said, and understanding the incident energy is all about risk assessment, and whether, you know, if you've got a visor that does fully enclose your head. I think in the videos that Marcin showed, you can see the arc blast. It can fully envelop your body, so that is the reason why they're saying wear the balaclava to protect any exposed skin at the back of your neck. So my recommendation would be, if your guys aren't comfortable wearing the balaclava, or they're not, is maybe select either, you know, they have to say you must wear the balaclava with the visor, or find another solution where that you can. The image I showed you was a baseball style hood, which should have total protection over the exposed skin, that's easy to wear. So it's find something that's appropriate and easy to wear, that your guys will support wearing.
I think the support wearing is a critical part, and so I think it's also important from a training perspective that wearers are aware of the risks that they're faced, and also the reasons why they're being asked to work as they are. So whether that be the actual way that they work, and also the PPE required, and so that there are very simple training tools available. Any quality vendor, you may say, should be able to provide complementary, that kind of material, that kind of simple instruction, which really clearly sets out what the risk is, what the PPE, your last line of defense, is designed to mitigate from, in a very simple, informative way that an engineer can relate to and understand and see the point of why they're being asked to do what they are. We're running on to time here. One question was about, I'm sorry, you probably understand this better than I would, Marcin. In DC N+N configuration, we are not loading each UPS more than 40%. And how can we achieve UPS maximum efficiency, whereas UPS OEM demand their UPS efficiency is 96%? I'm sorry, I'm a little bit lost.
I don't know. I have no idea how you can manage this.
Yeah, that's an efficiency question.
Yeah.
It's not really related to safety or arc flash. So because we're running a redundant system, you're not using the full ability of the UPS. If therefore the efficiency of the UPS is down. If you run a UPS fully loaded at 100%, it's the most efficient way to run it. Without knowing the UPS or the configuration, I couldn't really advise on that. And also, it's not really the topic of this Q&A.
Good. Quick another question here, Marcin, for yourself. In the UK, it is normal for an electrical safe system of work to be in place at data centers which appropriately train persons. Is this normal elsewhere? I could answer yes, pretty much to that, but.
Well, from my perspective, yes, it is. That's the rule of thumb that we have. If we have electricians, they have to be trained. If I go to Romania, Poland, or whatever it is, there's always electrician guy has to be trained at a certain level. So they have to be electrically, let's say, trained in general as electrical. And then all the things that Martin said, this comes internally.
Very good. Everyone, really appreciate the time to honor and respect the time you've all given up this morning, this afternoon, this evening, wherever you are. This is going to come to the end of our last and final 2020 non-commercial electrical safety workshop focusing on data centers. Next year, we'll be continue running with a series of these. And if you would be interested in participating either as an attendee or a panelist, then you can reach out to us. Also, there will be the contact details of some of our speakers will be circulated in a communication where a recording will be sent to each and every of you that have attended today, and also those that are registered but haven't managed to get on. And also, as I say, a CPD certificate. I think I've pretty much covered all bases. What I would say is we're coming towards the end of the year. We wish you a very, very happy Christmas time season, festive cheer for you all. But I would say that saving lives is the mission that the panelists and Skanwear as an organization have been on. So this webinar, as you are aware, is totally non-commercial and they are free to attend. So join the mission, saving lives. So with that, thank you and goodbye.
Goodbye.